All right, let's talk about one of the biggest challenges in cybersecurity today. How in the world do we build digital identities that are safe from the hackers we have now and also completely immune to the crazy powerful quantum computers of tomorrow? Let's dive right in.
I know. It sounds like some kind of magic trick, right? But believe it or not, this one question gets to the very heart of the biggest flaw in password security. See, every time you log into anything, you're fundamentally trusting that server with your secret. But what if you just didn't have to?
So, how do we pull this off? Well, the answer lies in a really fascinating piece of cryptographic technology. To get how it works, we need to talk about a powerful tool called an Oblivious Pseudo-Random function, or, OPRF for short.
Okay, so the keyword here is oblivious. An OPRF basically acts like a secure black box. Your device gives it some input, the server does a secret calculation with its own key, and then it hands you back a result, all without ever knowing what you sent it or what you got back. It's completely in the dark. And this diagram shows you exactly how that flow works. The client, that's C, doesn't just send its secret password over. No way. First, it disguises it, a process we call blinding. Then the server, S, does its thing on that blinded value with its own secret key. The absolute genius here is that nobody has the full picture. The server has no idea what your real password is, and you have no idea what the server's key is.
So it all boils down to this three-step cryptographic dance. First, you blind your secret. Imagine putting your password into a locked box that only you have the key for. Second, the server takes that locked box, adds its own secret sauce to it, and gives it back. And third, you use your key to unlock the box and get the final, super secure value. Blind, evaluate, unblind. Your actual password is never out in the open.
Okay, but you might be thinking, what's to stop the server from being sneaky? It could use different keys for different people to try and track them. Well, to stop that, we add a V for verifiable. A VORPF adds a clever bit of math called a zero-knowledge proof. This lets the server prove it used the one correct key for everyone without ever having to show you what that key is. It keeps the server honest. Now, this isn't just some crazy idea on a whiteboard. This tech is being used in the real world right now. Let's look at the OPEAK protocol. It's a modern standard for password security, and guess what's at its core? Yep, verifiable OPRFs.
This quote from Cloudflare really nails it. Instead of the server storing a hash of your password like they do now, it stores something we can think of as a secret envelope. And that envelope can only be opened with two keys at once: your password, which the server never ever sees, and the server's own secret key. And this leads to a pretty revolutionary idea, something that projects like Axiom are calling a vaultless passkey. Now think about this for a second. It means your private key, the thing that is digitally you, isn't actually stored anywhere. Not on your computer, not on a server. It's perfectly recreated from your password every single time you log in. It does its job, and then poof, it vanishes.
So this system is incredibly strong against any computer we have today. If a hacker breaks into the server, the database they steal is pretty much useless. But as amazing as this is, there is a massive, almost existential threat just over the horizon.
You see, the math protecting all of this stuff is basically a one-way street. It's incredibly easy to compute in one direction, but nearly impossible to reverse. For a normal, classical computer, figuring it out would literally take billions of years. It's that hard.
And then quantum computers enter the chat. A powerful enough quantum computer running something called Shor's algorithm doesn't just solve that math problem, it completely shatters it. The one-way street becomes a two-way highway. The entire security model would just be obsolete overnight.
So what do we do? How on earth do we build an identity system that's safe now and also safe in that quantum future? Well, this is where a really clever hybrid strategy comes into play. People have started calling it the sandwich approach, and you're about to see why.
It's an elegant, defense-in-depth sandwich. You take the whole VOPRF exchange, the filling, and you wrap it inside a secure tunnel. That tunnel, the bread, is created by a post-quantum algorithm, like Kyber. So the Kyber layer acts like quantum-proof armor for the whole conversation, while the VOPRF layer inside keeps doing its job of protecting your password from the server.
And what's so smart about this is that it recognizes you're fighting two different battles here. The Kyber part creates a secure channel. It protects the conversation while it's in transit. But the VOPRF part creates a hardened identity provider. It protects your password from the server and makes those offline guessing attacks impossible. You need both. This table just lays it all out. It really brings it home. Look, if you use Kyber by itself, yeah, it's quantum resistant, but it's terrible for offline attack protection. And the key is random every time, which is useless for an identity. Now, VOPRF alone, it's great against offline attacks and gives you a consistent key, but a quantum computer will eat it for lunch. It's only that hybrid approach, the wrapped VOPRF, that gets you a high on everything that matters.
Okay, we've waded through a lot of deep cryptography here. So what's the bottom line? Why should you actually care about this whole cryptographic sandwich?
It matters because this is how we can finally build a truly vaultless or zero material identity. It protects us from the massive server breaches that happen all the time, because even if they're hacked, there's nothing valuable to steal. And it protects us from that terrifying future threat of harvest now, decrypt later, where attackers are recording our data today, just waiting for a quantum computer to crack it tomorrow.
This hybrid approach gives us a powerful path forward. It's a blueprint for an identity that is truly, provably ours, one that can't be stolen from a server and can't be broken by the computers of the future. And that leaves us with one last big question. As our lives get more and more digital, how else can we apply these principles to secure, well, everything?